It is my immense pleasure to present this presentation for second semester students of our college, Kadir Muhyiddin College, Adaram. This presentation is about practical instruction, that is electrical experiments under cycle 1. In this cycle, I have to discuss 6 experiments, all are in syllabus, Bharat University syllabus. This slide shows syllabus of physical chemistry 2, practical of syllabus of our university for second MSc students in the 4th semester. And here in this cycle I have to discuss 6 experiments which are shown in the red color, that is conductometry acid base titrations and conductometry displacement titrations and conductometry solid product of sparingly soluble silver salt and verification of Ansagh equation by conductivity method and potentiometric titrations, acid base titrations and potentiometric titration, redox titrations. All these are discussed in this cycle. This slide shows a request to viewers. Here are first experiments, conductometric titration of mixture of acids, and aim of the experiment to determine strength of individual acids in a mixture of two acids which contains acid, weak acid and strong acid, and by conductometric titration using strong base and the standard ammonium chloride solution. That is, the students are given ammonium chloride salts and mixture of acids, weak acid and strong acid, and a link solution strong base. That is, the aim of the experiment is to determine the strength of strong acid and weak acid, the mixture of these two by titrating against strong base, which is standardized by standard ammonium chloride solution. That is the aim of the experiment, and principle of this experiment is the variation of conductance for the electrolyte is attributed to the removal of addition of ions. In the case of mixture of two acids, weak acid, strong acid, the strong base is first reacted with the strong acid present in the mixture, and the conductance decreases since the high mobility of H plus ion is removed as water by OH minus ion, that is from burette, that is added from burette. That is, HCl reacts with sodium hydroxide and the H plus ion of the strong acid is removed as water. That is why the conductance is decreased up to the end point. After the end point, the conductance is slightly increased. That is due to reaction of acetic acid in the mixture with the sodium hydroxide forming sodium acetate and water. And here the sodium acetate conductance is slightly higher than the acetic acid in the mixture. That is why the conductance is slightly increased. After the removal of acetic acid completely and adding sodium hydroxide, the conductance is increased rapidly due to high mobility of OH minus ion. So on adding sodium hydroxide after the end point, the conductance is increased due to increase of OH minus ion. So we get a graph, that is first conductance is decreased, afterwards conductance is slightly increased, afterwards conductance is increased rapidly. So we get three straight lines on extrapolating these straight lines, we get two intersection of these three straight lines. First intersection corresponds to the amount of sodium hydroxide occurred to neutralize the HCl in the mixture, and the second intersection corresponds to the amount of sodium hydroxide occurred to neutralize both HCl and acetic acid. So from these two intersection points, there is a corresponding volume of sodium hydroxide, we can calculate the strength of strong acid in the mixture, and we can calculate strength of weak acid in the mixture. Here the materials record, that is conductivity cell, conductivity meter, mixture of acids, sodium hydroxide, link solution and ammonium chloride for preparing standard solution. Procedure of the experiment. A standard solution of 0.02 N ammonium chloride solution is prepared by weighing accurately the record amount of ammonium chloride and in a 100 ml SMF and make use of conductivity water. And 40 ml of this solution is pipetted out into a clean beaker, and the cell, conductivity cell is washed with water and rinsed with the distilled water, and then the conductivity cell is dipped in the ammonium chloride solution and connected to conductivity meter. And the sodium hydroxide solution is taken in the burette And from the burette, 0.5 ml portion of the solution is added to ammonium chloride and stirred well, and the conductivity of the solution is measured. And on adding 0.5 ml, 0.5 ml portion of sodium hydroxide, the conductance value is decreased due to removal of ammonium ion as ammonium hydroxide, which has low ionization. So the conductance is decreased up to the endpoint. Afterwards, the conductance is increased due to increase of OH minus ion, which has greatest mobility. And the conductance readings are taken after the endpoint. For 5 or 6 readings are taken, and we plot, and we plotting conductance versus volume of sodium hydroxide. We get two straight lines. On connecting all the conductance value by scale, we get the two straight lines, and the point of intersection corresponds to the volume of sodium hydroxide, which is required to neutralize 40 ml of 0.02 normality ammonium chloride. From this, the strength of sodium hydroxide is calculated. The burette is filled with the same sodium hydroxide solution, and the given acid mixture, that is, which contains strong acid, weak acid, that mixture is made up to 100 ml by make use of conductivity water. And from this solution, 40 ml of the solution is pipetted out into a clean beaker, and the conductivity cell is dipped after washing and the rinsing with the conductivity water, and the conductance of the solution is measured, and on adding sodium hydroxide 0.5 ml portion of sodium hydroxide from burette, and the conductance in the solution is stirred over and conductance is measured. The readings are taken up to 24 ml, and the conductance values are decreased due to removal of H plus ion of the strong acid, and after the removal of H plus ion, the conductance value is slightly increased due to reaction of sodium hydroxide with acetic acid, forming sodium acetate, which has slightly higher conductance than acetic acid. So the conductance value is slightly increased up to the neutralization of acetic acid. After the endpoint, the sodium hydroxide, on adding sodium hydroxide, the conductance value is increased due to increase of OH minus ion. So on plotting conductance versus volume of sodium hydroxide, we get three straight lines, and the point of intersection, first one corresponds to volume of sodium hydroxide required to neutralize HCl in the mixture, and the point of intersection of second one, that is second and the third straight line, a point of intersection, that is the volume of sodium hydroxide required to neutralize both HCl and acetic acid in the mixture. Suppose the first endpoint is Vx and second one is Vy. By using Vx, that is volume of sodium hydroxide required to neutralize HCl, that is that volume Vx, and from the strength of sodium hydroxide and from the volume of the mixture, that is 40 ml, we can calculate strength of HCl in the mixture. Similarly, Vy minus Vx, that volume corresponds to a volume of sodium hydroxide required to neutralize acetic acid in the mixture. So by knowing the volume Vy minus Vx and the strength of sodium hydroxide and the volume of mixture of acid 40 ml, we can simply calculate the strength of acetic acid in the mixture. These are about conductometric titration between strong mixture of acids and sodium hydroxide. Here in this slide, model graphs are shown, and also the tabular columns and nature of calculations, and the results are also shown in this slide. What are the results? One is the strength of sodium hydroxide, another one is strength of HCl in the mixture, and the third one is strength of acetic acid in the mixture. That's all. Next experiment number 2, determination of equivalent conductance of strong electrolyte at infinite dilution and verification of De-Hcl Ansatz equation. Aim of the experiment to determine the equivalent conductance of a given strong electrolyte such as KCl, NaCl, HCl, potassium nitrate at various concentrations and at infinite dilution, and verification of De-Hcl Ansatz equation. That is the aim of the experiment. And the principle of the experiment, according to Arrhenius theory, conductance is due to number of ions. But in the case of strong electrolytes, the electrolyte is completely dissociated even at ordinary concentrations, but also the conductance is increased on increase of dilution. So the increase of dilution is not due to number of ions, that is due to mobility of ions. That is that was given by Debye and he derived an equation. That equation is called as Debye equation, which is modified by Onsager scientists. That is called the final equation is Debye-Onsager equation. So Debye-Onsager equation, that is lambda c, that is equal to lambda 0 minus a plus b lambda 0 root c. So this equation is in the form of straight line equation. So on plotting lambda c versus root c, we get a straight line with a negative slope, and extrapolating the straight line to zeroth concentration, we get the value of lambda 0 of the given electrolyte. That is the principle of experiment. So here the materials required for the experiment: conductivity, meter, strong electrolyte like KCl, and the conductivity cell, conductivity, water, thin glass rod, SM of 100 ml, and SM of 200 ml, SM of 1. These are the materials required for the experiment. A procedure of the experiment: exactly n by 5, that is 0.2 normality KCl solution is prepared by weighing required amount of KCl in a 200 ml SMF, and the solution is prepared with distilled water. That is a bulk solution. From this solution, number of diluted solutions are prepared. That is diluted solutions with the concentration n by 10, n by 20, n by 40, n by 50, n by 100, n by 200. That is, these solutions have the concentration, that is 0.1 normality, 0.05, 0.025, 0.02, 0.01, 0.005 normal solution. Now we have totally 7 solutions, that is 6 diluted solutions and 1 bulk solution, that is 0.2 normality solution. So for these solutions, the conductance are measured by make use of conductivity cell and the conductivity meter. For that, about 50 ml of this solution is taken in a beaker, and the conductivity cell is dipped after washing and rinsing with the distilled water and connected to conductivity meter, and the conductance of the solution for these solutions are determined or measured. The cell constant of the given conductivity cell is also determined from the conductance value of 0.1 normal KCl solution, and from the 0.1 normal T KCl solution conductance, the cell constant is determined by the formula: cell constant is equal to specific conductance of 0.1 normal KCl solution divided by observed conductance of 0.1 normal KCl solution. The specific conductance of 0.1 normal KCl solution, that value is constant, that is 0.01412 moles per centimeter. By simply substituting this value, specific conductance, and which is divided by observed conductance of 0.1 normal KCl solution, we can simply calculate the cell constant of the given conductivity cell. From the cell constant value and the conductance of various solutions, the specific conductance of the solution is calculated by simply multiplying cell constant with the conductance of the solution. And from the specific conductance, the equivalent conductance value is calculated. The formula lambda c is equal to 1000 into K divided by C. Here K is the specific conductance and C is the concentration of the solution. Concentrations, that is like 0.1, 0.05, 0.025, 0.02, 0.01 and 0.005, and also the bulk solution concentration 0.2n. So we can calculate lambda c values for these solutions, and the values are tabulated in the tabular column, which is shown in this slide. And on plotting lambda c versus root concentration, we get points, and connecting all the points we get a straight line, and extrapolating the straight line to zeroth concentration we get the lambda 0 value. So in this way we can calculate lambda 0 value, and the formation of straight line on plotting lambda c against root c proves the Debye-Onsager equation. So that is a result of the experiment, that is equal conductance of the even strong electrolyte at infinite dilution. That is one result. Another result is formation of straight line on plotting lambda c against root c proves the Debye-Onsager equation. These are about determination of lambda 0 of strong electrolyte, and verification of Debye-Hückel-Onsager equation. That's all. That's the third experiment, solubility product by conductivity method. Aim of the experiment to determine the solubility product of sparingly soluble salt by conductivity method. And principle of the experiment, salts like AgCl, barium sulfate, lead chromate, etc. These salts are sparingly soluble in water. That is, the solubility of these salts are determined by conductance measurement. That is, at infinite dilutions, these salts give the concentration that is called solubility. That is, lambda 0 is equal to K into 1000 by S, where S is the solubility and lambda 0, that is the equivalent conductance of these sparingly soluble salts at infinite dilution. So that is lambda 0 value, that is calculated by adding ionic conductance of the ions present in the sparingly soluble salt. So by measuring experimentally the conductance of the solution given by the salts at infinite dilutions, and by knowing lambda 0 value, we can simply calculate the S solubility by the formula S is equal to 1000 into K divided by lambda 0. And here the K is the specific conductance of the salt, sparingly soluble salt. Next, procedure of the experiment, about 1 or 2 grams of sparingly soluble salt is added to about 100 ml of water and stirred well for some time using glass rod. It is then allowed to settle. The supernatant solution is drained and about 100 ml of water is again added to salt and stirred well for some minutes and drained. The process is repeated more than 5 times, more or 5 or 6 times, and finally the filtered in a clean dry beaker, and the conductance of the solution is measured using conductivity cell of known cell constant connected to a conductivity meter, and the conductance of water used to prepare the solution is similarly measured using the same conductivity cell. And from this, the conductance of the sparingly soluble salt solution and the conductance of water, the conductance of sparing salt only is calculated by simply subtracting conductance of water from the conductance of salt solution, and from the conductance of sparingly soluble salt, the specific conductance is calculated by simply multiplying the conductance with the cell constant. From this specific conductance and lambda 0, which is known, the solubility is calculated using the formula solubility is equal to K into 1000 divided by lambda 0. In this way, the solubility of the sparingly soluble salt is calculated, determined, and the product of this, the solubility that is solubility score, that gives the solubility product of the sparingly soluble salt. These are about sparing determination of solubility of sparingly soluble salt and the salt product of sparingly soluble salt. In the next slide, calculation part and the result of the experiment all are given in the next slide. This slide shows clearly calculation about this experiment, that is conductance of sparingly soluble salt solution, that is experimentally determined, and also conductance of pure water is also determined. From that, conductance of sparingly soluble salt only, that is calculated by simply subtracting conductance of pure water from conductance of sparingly salt solution. That gives the conductance of sparingly soluble salt. From that, specific conductance is calculated by simply multiplying with the cell constant, and from the specific conductance, the solubility is calculated by the formula S is equal to 1000 into K, that is specific conductance of sparingly soluble salt only, divided by lambda 0, and the lambda 0 value, that is the equivalent conductance of the salt solution, equivalent conductance at infinite dilution, that is determined by simply adding ionic conductance of the ions of the sparingly soluble salt, and on substituting lambda 0 value, we can calculate solubility and the square of solubility, that is solubility product, and the result of the experiment. One is the solubility of sparingly soluble salt Another one is the solid product of sparingly soluble salt like AgCl, AgI, barium sulfate, etc. Next one is fourth experiment, conductometric titration of acetic acid sodium acetate mixture with acid and base. The aim of the experiment to determine the strength of acetic acid and sodium acetate in the given buffer solution by conductometric titration using strong base and strong acid. And the principle of the experiment, the variation of conductance for the electrolyte is attributed to the removal of addition of ions. In the case of mixture of acetic acid and sodium acetate, the strength of acetic acid is determined by titrating with the strong base, and the strength of sodium acetate is determined by titrating with the strong acid. That is, the weak acid, acetic acid, is reacted with the base. The conductance slowly increases since the formation of salt of the acid, say acetic acid, has greater conductance than acetic acid. That is, acetic acid, that is a weak acid, degree of dissociation is low, and it reacts with sodium hydroxide forming sodium acetate, and this salt has somewhat greater conductance of acetic acid. That is why there is a slight increase in the conductance, and after the removal of complete acetic acid completely on adding sodium hydroxide, conductance is increased rapidly due to increase of OH minus ion. So we get two straight lines on connecting the points and the conductance values on plotting conductance versus volume of sodium hydroxide, and the point of intersection corresponds to the amount of sodium hydroxide required to neutralize 40 ml of acetic acid in the buffer solution. So in this way we can calculate the strength of acetic acid in the buffer. Similarly, the strength of sodium acetate is determined by titrating the 40 ml of buffer with HCl solution. That is, sodium acetate reacts with HCl, forming sodium chloride. Here also the sodium chloride has somewhat slight greater conductance than sodium acetate. That is why there is a slight increase in the conductance up to the end point. After the end point, on addition of HCl, the conductance increases rapidly due to increase of H plus ion. So we get two straight lines, and the point of intersection corresponds to the end point. From the end point, the strength of sodium acetate in the given buffer solution is determined. That these are about the principle behind the experiments, and materials record for the experiment: conductivity cell, conductivity meter, mixture of sodium acetate and acetic acid buffer, that is buffer, and 0.1 sodium 1 n sodium hydroxide and 0.1 n HCl. Next, procedure of the experiment. The given buffer solution, which contains acetic acid and sodium acetate, that solution is made up to 100 ml in a 100 ml SMF using conductivity water, and 40 ml of this solution is pipetted out in a clean beaker, and it is initially diluted such that a conductivity cell is immersed in it using conductivity water. The cell is connected to a conductivity meter and the conductance is measured. Sodium hydroxide solution, that is 0.1 n sodium hydroxide solution, is taken in the burette after washing with the distilled water and rinsing with the sodium hydroxide solution. And from the burette, 0.5 ml portion of sodium hydroxide is added to the 40 ml of the buffer solution, and the solution is stirred well and the conductance is measured, and the conductance values are measured up to the volume of 16 ml, and the conductance is plotted against volume of sodium hydroxide. The point of intersection of two straight lines gives the end point, and hence from the strength of sodium hydroxide and the strength of sodium acetic acid, that is weak acid in the buffer, that can be calculated by knowing the volume of sodium hydroxide required to neutralize the 40 ml of buffer solution. Now the beaker is washed with water, and 40 ml of the given buffer solution is again pipetted out in the clean beaker, and it is initially diluted such that conductivity cell is immersed in it using conductivity water, and the 0.1 n HCl solution, that is taken the burette after washing the burette with water and rinsing with 0.1 n HCl solution. From the burette, 0.5 ml portion of HCl is added to the 40 ml of the mixture and stirred well, and the conductance is measured. The conductance readings are taken up to the volume of HCl 16 ml. Now on plotting the conductance of HCl, these are not HCl, conductance of the buffer versus volume of HCl, you get two straight lines, and the point of intersection corresponds to the volume of HCl, volume HCl required to neutralize 40 ml of sodium acetate in the buffer. So by knowing the strength of HCl and the endpoint and the volume of buffer taken 40 ml, we can calculate the strength of sodium acetate in the buffer. And here are the calculation part, model graph, and the result of the experiment all are given. Now what is the result? Result one is strength of acetic acid in the buffer solution, another is strength of sodium acetate in the buffer solution. These are about the experiment, that is conductive titration between buffer versus HCl and buffer versus sodium hydroxide. That's all. The next fifth experiment, potentiometric titration of ferrous sulfate solution. Aim of the experiment to determine the strength of given ferrous sulfate solution potentiometrically using an approximately 0.1 normal potassium dichromate solution as the link solution and standard solution of ferrous sulfate solution. Here two solutions are given. One is a standard solution of ferrous sulfate, another one is given solution of ferrous sulfate, and also potassium dichromate of approximately 0.1 normality. That our solution is also given. So here the aim of the experiment to determine the strength of given ferrous sulfate solution potentiometrically by titrating the solution against 0.1 normal potassium dichromate, and the dichromate is standardized by a standard solution of ferrous sulfate solution potentiometrically. That is the aim of the experiment. And principle behind the experiment, the reaction between dichromate and ferrous, that reaction is given in this slide, and the potential of the platinum electrode, which depends initially on the concentration of Fe2 plus and Fe3 plus. So after the complete neutralization of Fe2 plus, there is no formation of Fe3 plus. So after the end point, the potential of the electrode depends upon the concentration of Cr2O2 minus and the Cr3 plus. So there is a sudden change in the EMF near the end point, and the end point first it gives the end point range, and the exact end point is determined by more addition of potassium dichromate near the end point. There is 0.2 ml addition of potassium dichromate. These are the principle behind this experiment. Next procedure of the experiment, 20 ml of standard ferrous sulfate solution taken in a clean beaker to which one test tube full of 2N sulfuric acid solution is added. A platinum electrode and calomel electrode. These electrodes are dipped in the solution after washing with the distilled water, and the platinum electrode is connected to the positive terminal of the potentiometer, and the initial EMF of the cell is noted, and the potassium dichromate solution is taken in burette after washing and rinsing with potassium dichromate solution, and from this burette 2 ml portion of dichromate solution is added to ferrous sulfate solution and stirred well, and the EMF of the solution is noted. After each addition, the reaction mixture is stirred well, and 2 ml portion of the solution, dichromate solution, is added, and the readings are taken up to a sudden change in the EMF, and afterwards 3 more readings are taken. The volume corresponds to sudden change, that is endpoint range, and the experiment is repeated by again pipetting 20 ml of the standard ferrous sulfate solution in a clean beaker, and the experiment is done as before, and by the 0.2 ml portion of dichromate near the endpoint range. Suppose the endpoint is 18 to 20, then the solution is added up to 17.6, and afterwards 0.2 ml dichromate solution is added, and the EMF readings are noted. And here also there is a jump in the EMF. After getting the jump, 4 or 5 readings are taken, and from this the exact endpoint is determined from graph. The EMF values on adding 2 ml portion of potassium dichromate solution is recorded in table 1, and on adding 0.2 ml addition, the EMF values are put in the table 2. And on using table 1, a graph is plotted between volume of potassium dichromate and EMF. And here this graph shows the endpoint range. And from the table 2, another table number 3 is constructed by taking average volume of potassium dichromate and difference in EMF and delta E by delta V, and a graph is plotted against average volume of potassium dichromate and delta E by delta V, and this graph is a derivative graph, and this graph contains a peak, and the volume corresponds to the peak. That is the correct endpoint. And thus by knowing the endpoint, that is volume of potassium dichromate and volume of parasulfate 20 ml and the strength of parasulfate, we can calculate the strength of potassium dichromate. These are about standardization of potassium dichromate. Next, the given solution, unknown ferrous solution is made up to 100 ml, and from this solution 20 ml of given ferrous sulfate, that is unknown ferrous sulfate, is pipetted in a clean beaker, and the platinum and the calomel electrodes are dipped, and the readings are taken as before. And here also the EMF values on adding potassium dichromate, that is recorded in the table 4, and on adding 0.2 ml addition, the EMF values are noted in another table, that is table 5, and table 6 is constructed from table 5 on plotting EMF versus volume of dichromate on using table 4. We get a graph which shows the endpoint range, and on plotting delta E by delta V against average volume of potassium dichromate, that gives a peak, gives a curve which peak, and the volume corresponds to the peak, that is the endpoint. From the endpoint, that is the volume of potassium dichromate and the strength of dichromate and volume of unknown ferrous sulfate pipetted out, and we can calculate the strength of given unknown ferrous sulfate solution. So these are about procedure about this experiment. This slide shows table 1, table 2, table 3, table 4, table 5 and 6, and also the nature of the graph of 1. And here the tables are actually, that is a lengthy table, and here the volumes of potassium dichromate is 0, 2, 4, 6, 8, 10, up to the end point. Afterwards there are 3 readings. So all these are shown, the tables are shown in this slide. This slide shows nature of calculations, nature of graph 2, and the result of the experiment. The result of the experiment, that is strength of linked potassium dichromate. Another result, that is strength of given ferrous sulfate. These are about estimation of ferrous sulfate by potentiometric titration. The next one is potentiometric titration of mixture of acids. Aim of the experiment to determine the individual strength of strong acid and weak acid in the given mixture potentiometrically using an approximately 0.1 n sodium hydroxide, and the sodium hydroxide is standardized by using standard solution of HCl 0.1 normally HCl solution potentiometrically. That is the aim of the experiment. Next, the principle of experiment, an acid-base titration can be carried out potentiometrically with an electrode which is reversible with respect to H plus ion, and such as glass electrode, hydrogen electrode, and quinhydron electrode. In this experiment, quinhydron electrode is used, and quinhydron electrode is nothing but a platinum electrode with a pinch of quinhydron substance in the solution. Now the setup, that is called quinhydron electrode. This quinhydron electrode can combine with the standard calomel electrode, and the cell setup is shown in the slide, and the cell potential equation is also given. As such, on adding sodium hydroxide from the burette to the H plus HCl solution, acid solution, the H plus ions are removed and the EMF decreases slowly. But at the end point, there is a sudden change, sudden decrease in the EMF. Afterwards, 3 more readings are taken, and from the sudden change, and the experiment is repeated, and once again with sodium hydroxide as HCl titration. By adding very small portion, 0.2 ml portion, we can determine the exact endpoint from the derivative curve. Next, procedure of the experiment: 20 ml of standard HCl of strength 0.1 n, that is taken in a beaker, and in a clean beaker right with a glass rod, and the solution is saturated with a pinch of quinhydron substance, and platinum electrode and calomel electrode. These are dipped in the solutions and connected to potentiometer. And the burette is filled with the lean sodium hydroxide solution after washing and rinsing with sodium hydroxide. From the burette, 2 ml portion of sodium hydroxide is added to acid solution and stirred well, and the EMF of the reading is noted and recorded in the table 1, and again 2 ml portion of the sodium hydroxide is added and stirred well, EMF reading is noted, and these readings are taken up to a sudden change in the EMF. Afterwards 3 more readings are taken. The EMF values on addition of 2 ml portion of sodium hydroxide, and the values are noted in the table 1, and 0.2 ml addition of sodium hydroxide EMF values are noted in table 2. And in both the cases, ACP, single electrode potential, that is single electrode potential of ion hydrogen electrode, that is calculated by the formula, that is ACP is equal to minus 0.2397 minus EMF. Minus 0.2397, that is single electrode potential of calomel electrode. Actually, the EMF is the potential difference, and the potential difference of these two electrodes, ion hydrogen electrode and calomel electrode. And so the single electrode potential of ion hydrogen electrode, that is given by the formula minus 0.2397 minus EMF. So in both the cases, table 1 and table 2, ACP values are calculated and recorded. And from the table 2, table 3 is constructed by taking average volume of sodium hydroxide, delta ACP, and delta ACP divided by delta V. And here delta V, that is change in volume, that is 0.2 ml. And a graph is plotted using table 1, which shows the endpoint range. And another graph is plotted against average volume of sodium hydroxide, delta ACP, delta V, which shows a graph, the peak, that is a derivative graph, that derivative curve, and the volume corresponds to the peak that gives the endpoint, that is the volume of sodium hydroxide required to neutralize 20 ml of standard HCl solution. From this, that is the volume of sodium hydroxide, and the volume of HCl taken 20 ml, and the strength of HCl 0.1 normality, the strength of sodium hydroxide is calculated. These are about standardization of sodium hydroxide by using standard HCl potentiometric method. The given mixture, which contains the strong acid and weak acid, that mixture is made up to 100 ml using distilled water in a 100 ml SMF. From this 20 ml of the mixture is prepared out in a clean beaker, and the electrode and calomel and a pinch of quinine substance, these are added as before. And the titration, the same procedure is repeated for getting the endpoints, but here two endpoints are obtained. First one corresponds to strong acid, and continuing the titration we get another endpoint. That endpoint, that range corresponds to both the volume of HCl and acetic acid. Once again, the experiment is repeated for getting correct endpoint. That is first endpoint, that is the volume of sodium hydroxide required to neutralize 20 ml of HCl in the mixture. And second endpoint corresponds to volume of sodium hydroxide required to neutralize both HCl and acetic acid in the mixture. So the tables, 2 ml addition of sodium hydroxide, the EMF values are noted in the table 4, and 0.2 ml addition is recorded in the table 5. And from this, table 6 is constructed. From table 6 is constructed by taking average volume of sodium hydroxide and delta ACP and delta ACP divided by delta V. So on plotting ACP versus volume of sodium hydroxide from graph 4, we get two ranges, two endpoint ranges, two endpoint ranges, and on plotting average volume of sodium hydroxide and delta ACP divided by delta V from using table 6, we get two peaks. One peak corresponds to volume of sodium hydroxide required to neutralize HCl. Another one is corresponds to both acids, HCl and acetic acid. So on subtracting, that is volume of sodium hydroxide required for HCl from volume of sodium hydroxide from for both the acids, HCl and acetic acid, we can calculate volume of, you can calculate the strength of acetic acid in the mixture, and from the first endpoint the strength of HCl is calculated. So all these are shown in the next slide, and here result of the experiment, strength of sodium hydroxide and strength of HCl in the mixture, and strength of acetic acid in the mixture. These are about the experimental procedures and the result of the experiment. This slide shows tabular column and nature of calculation part, and there is standardization of sodium hydroxide, estimation of mixture. There is to determine the strength of HCl in the mixture, to determine the strength of acetic acid in the mixture. This slide shows the graphs obtained in this experiment. Graph 1 is the graph for titration between standard acid and sodium hydroxide, and this graph shows the endpoint range. And graph 2 is the graph obtained by using the table 3. This graph clearly shows the endpoint, that is a peak, that is a volume of sodium hydroxide corresponding to the peak, that is the endpoint. That is a volume of sodium hydroxide required to neutralize the standard acid, 20 ml of standard acid. And graph 3 is obtained in the titration between mixture of acid and sodium hydroxide. This graph shows two endpoint range. First range corresponds to HCl in the mixture. Second endpoint corresponds to HCl and acetic acid in the mixture. And graph 4, that is a derivative curve, corresponds to two endpoints. First endpoint Vx, second endpoint Vy. That is Vx is the volume of sodium hydroxide required to neutralize the HCl in the mixture, and Vy, that is the volume of sodium hydroxide required to neutralize both the HCl and acetic acid in the mixture. Therefore, Vy minus Vx, that is the volume of sodium hydroxide required to neutralize the acetic acid in the mixture. This slide shows some of the model questions which are frequently asked in the university practical examination. This slide shows the questions, model questions, which are frequently asked in the university examination. That is a continuation of previous slide. With this, I want to conclude my lecture on practical instruction about electrical experiment under cycle 1. I think this presentation is more useful for second MSc students, and I think it is this presentation is more useful to prepare Viva questions related with the experiment. I wish all the students all success. I express my sincere thanks to all. Thanks, one and all.